Hello, and welcome back to CS631 Advanced Programming in the Unix Environment. So far, we've talked a lot about individual programs, such as the common Unix utilities found under /bin, but we really haven't talked much about processes. Well, we did mention in our introductory lecture that a process has certain properties, such as a process ID. We've seen that a process has an effective UID and group ID, and we've noted that properties of a process cannot be changed by a child process, such as the current working directory. But we really have not looked at all at what a process really is, what it looks like, or how processes are brought to life and how they die. In these coming videos, covering the materials for week number 6, we will do all that. But first, let us get a visual understanding of what a process looks like in memory. This can be quite useful to understand many aspects of process execution later on. I'm sure you've seen an illustration of a process in memory like this before, where we show a high address, a low address, the stack, the heap, etc. But we generally like to really see what things look like, by writing some code and inspecting the outcome. How can we do this? Well, let's take a look. For starters, let's note that in C we are sufficiently low level that we can inspect the address of any program element even without using a debugger. Every variable really is just whatever is stored at a given memory location, with the amount of memory used being defined by the type of the variable. A pointer, in turn, is nothing but a variable whose value is an address in memory. By using the ampersand operator, we can dereference a variable. That is, instead of a value stored at the given address, we get a pointer to the address of the variable. We can then take this memory address, cast it to a number, and print that value in hex. Here we go. So apparently, the variable var inside of main can be found at this hex address. So now that we've seen how to do that, let's try to use this to explore a little more about our program. Here, we see two arguments being passed to our main function, argc and argv. We declare a private variable visible only within main, but we also have a global variable, accessible to any function in our program, even if we only have one function here, named main. But since this is C, we are not bound to dereferencing variables. We can also dereference function names, thereby obtaining a function pointer and print that address. So when we run this program, the output looks like so. And this is now getting a bit closer to what we imagined our process to look like, with some things being found at a high address, argc, argv, and the private variable in this case, and some things found at a notably lower memory address, our global variable and the function main itself. But that's not enough. We want to further see if we can identify the location of the stack and heap and some of the other segments of the program in memory. So here we have a more comprehensive program that declares a number of different things and prints their respective memory addresses. Here we have a few variables declared. Note that some of them are initialized, meaning they have been assigned an explicit value, and some of them are uninitialized. Our main function has some variables visible only to main, and we then begin printing out the various addresses. From within main, we then call two other functions. Then we dynamically allocate a bit of memory via malloc, and continue printing other addresses. Don't worry too much about reading the code here. You can download it from the course website to play around with yourself. Let's run it. Here's the output this program produces, nicely formatted to help us better understand where the different memory addresses are. This looks a little bit more like what we had previously visualized. Notice how the output is mostly sorted by memory address, starting with the highest address at the environment and down to the lowest address of the main function itself. Since we invoked the command without any additional command line parameters, argv will contain two elements, argv0, the program name, and null. Each member of argv is a star, pointer, and thus takes 8 bytes, which we can see here. So our findings match our illustration. Command line arguments and environment variables are found at the high address of the process in memory. At the bottom, the low addresses, we find the text segment. This is the part of the virtual address space that contains executable instructions. This is usually marked read-only. This, by the way, is where the original use of the sticky bit comes in. If that bit is set in the ST mode, then the OS can keep the text segment in swap space after the process terminates. Upon a subsequent execution of the same command, the kernel can then simply move the segment from swap into real memory, which is much faster than fetching it from disk. That is, the text segment remains sticky in memory, and this is why the sticky bit is also known as the save text bit. This used to be set on certain large, frequently invoked binaries, the compiler say, or Emacs. Most modern Unix versions do not use a sticky bit on files any longer. Next, going bottom up, we have our initialized data, that is, variables that we have defined and declared in global scope, or that are static variables even if defined within a function, meaning they retain their address across function invocations. This is the initialized data, or simply data segment. Both the text segment and the data segment are read from the program file by exec at program startup time. After that, we see the part where we store uninitialized data. Here we can see our globally declared but uninitialized array size, which is what we declared to be 16 bytes, which is nicely reflected in the hex address, showing the start of the array at 601A0 and ending 16 bytes higher at 601A-B0. All of the uninitialized global variables end up in this segment, the uninitialized data segment, also known as the BSS segment, as it is placed after the block starting symbol. This also includes static variables that have been initialized to 0, or other uninitialized variables are initialized to all bit 0 by exec. Next, on top of the BSS segment sits the heap. This is where memory is dynamically allocated from at runtime, on demand, via malloc or similar functions. This area is shared by all threads, shared libraries, or dynamically linked modules in the given program. We allocated 32 bytes, which we can again see as the starting address ending in 00 increased to 20 hex. As additional memory is allocated, the heap grows upwards towards the higher addresses. Now, back up towards the higher addresses, right below where we found our command line arguments, the stack begins. The stack is a LIFO, a last in, first out, well, stack, on which the function frames are pushed as they are executed. The stack pointer points to the top of the stack, which, somewhat confusingly, is the lower address in this visualization. Sometimes you may encounter this illustration flipped upside down, so as to allow the stack pointer to actually point to the visual top of the stack, but for this architecture that then places the high address at the bottom. I find that even more confusing and prefer this image here instead. You get used to saying top of the stack when pointing at something that grows downwards, don't worry. Anyway, so the stack starts at the higher address, and so all the addresses in the stack decrease in order. We find our first variable on the stack, the int var, at A8254. As an int, it only requires 4 bytes, so the next variable, the array we declared inside of main, begins at A8250, which at 16 bytes ends at A8240. Note also that argc and argv, the arguments to main, are also found here, and everything belonging to this function goes into this frame on the stack over here. Now from within main, we call func2, which gets pushed on the stack, and our stack pointer is updated. After func2 completes, we pop the frame of the stack and return back to main, with the stack pointer back here. Now we call func, which is pushed onto the stack. Func calls func2, which gets pushed onto the stack as well. So we saw how while the heap grows up from a low address, the stack grows down from a high address, as function frames are pushed onto the stack. But notice that we have one outlier here on the left. Within our function func, we declared a static int n equals 1. As a static variable that was initialized, we should find this address in the data segment down here. If you were to flip the initialization of this variable to 0 in the code, you should see that this flips the address to end up in the BSS segment. Give it a try. Alright, so now let's take a look at our process image in memory. As we said, the heap grows up and the stack grows down. But that means that the two are growing towards one another. So what happens if you keep pushing more and more frames onto the stack? Let's give it a try. We've modified our program to allow a compiler flag to have func2 call func, thereby causing infinite recursion. If we compile it normally, everything behaves as before. But if we define stack overflow, then we eventually get a seg fault. That's right, a segmentation violation, because we are accessing a segment we have no business accessing. Let's take a quick look how this happened. We start out and call func, which calls func2, which then calls func, which calls func2. And so on, 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 over 43,000 times, until eventually we overflow the stack into an area that it has no longer any business reaching into. We segfault due to a stack overflow. And now that you know why that website from which you copy all your code examples has that name, I think we can take a break. I hope that the illustration of the process layout in memory was useful to you. We'll get back to this every so often throughout the remainder of the semester. Make sure to download the source file for the program and play around with the results, and read through the related links shown here. Next time, we'll talk a bit more about how the process starts and how we enter the main function. Until then, thanks for watching. Cheers!